Welcome back, class, to our course on mechanical behavior of materials part 2. So in the last lecture, we started talking about fatigue testing. And in today's lecture, we will talk more about factors which affect fatigue behavior as well as Ascent. Okay, so let's proceed. So we discussed about different type of fatigue cycles. So if you remember, there was random stress cycles, then completely reverse stress cycle where R was equal to -1, and then repeated cycle. R can be different values. It can be negative, it can be positive. Okay. So we had discussed this. I just wanted to show you a schematic again. Okay, so what are the different factors which can affect fatigue failure? So the first one is obviously the process parameters. Okay. So in the last lecture, we discussed about stress parameters, right? So those are the parameters which can obviously going to affect the fatigue failure of a material, right? So basically three factors play important role. The first one is the maximum stress. Okay. The second is magnitude of variation in stress. Okay. That means sigma R. Okay, or sigma amplitude. And the last one is the number of cycles. So if you remember, if you have a fatigue cycle like this, so this stress is your maximum stress, and then you have sigma R, which is stress range, and then you also have sigma A, which is the amplitude, right? So if you increase the maximum stress, right, it will be easy to fail during fatigue. That is point number one. Similarly, if you increase the magnitude in variation in stress, that means if you increase the sigma R, it will be easy for fatigue damage, right? For the accumulation of fatigue damage, or it will be easier for fatigue failure, right? And third is the number of cycles. The more number of cycles you have in a fatigue cycle, there will be more damage accumulation. Okay. So this is point number one, which is related to process parameters. Second is geometrical. Okay. Especially anything on the surface, right? Scratches, grooves, etc. They are going to significantly affect the fatigue failure behavior. So anything on the surface that is a site of stress concentration will affect fatigue behavior, especially the track initiation. We'll discuss about track initiation and propagation. Okay. And what are those sites? sides. So, those can be notches, cracks, scratches, etc. Okay. Now you know that if you have a notch, then there will be stress concentration, right? And if there is a stress concentration, you require a smaller amount of stress for failure to occur. That much we have studied, right? And depending upon the size of the notch or the crack on the surface, the stress concentration magnitude also varies, right? So obviously it is going to affect the fatigue behavior. So that is point number 2. Third is materials and microstructural aspects. So this is about the composition. So obviously, if you are going to change the composition, the fatigue deformation behavior is going to change. Then grain size is also going to affect residual stresses. So all metallurgical factors, right? These are going to affect the fatigue deformation, right? Or fatigue behavior. The last is your environment. So if you have a corrosive environment and fatigue loading is also there, your material is going to fail earlier. Okay. So a corrosive environment can have a deleterious interplay with fatigue. Okay, and this is called corrosion fatigue. Okay, so if you have a presence of corrosive environment, your material is going to fail earlier in fatigue. Okay. Now let's talk about the Ascent curve. So if you remember, we had discussed the unnotched specimen and notched specimen. And when we have unnotched specimen, we always talk about Ascent curve. Okay. So before that, let me tell you what are the different equipments we can use to do fatigue testing. So this is called RR mode reverse bending fatigue test. And when we say reverse bending fatigue test, we know R is equal to going to be -1. Okay, that means sigma maximum is going to be equal to sigma minimum with a negative sign. Okay, so this was the first fatigue test machine developed. Okay, where R is equal to -1. And this is what we have in our lab. Okay, and if you see the magnified version of the loading, so here you have a load where you place different load depending upon the requirements. Okay, and then you can place your sample here in the right image I'm drawing, right? So here you can place your sample. Okay, and then these two are your main bearing support. Then you have a coupling. Load I have already mentioned, it is on the left side, you can see. Okay. Overall, what you have is 4-point bending configuration. Okay. So you have loads like this. And this is your sample here. And the sample is typically hourglass as shown here. So probably in the next lecture, I'm going to show you different specimen also. CT, flat dot bone, round dot bone, then hourglass samples. Physically, I'm going to show you so that you have better understanding. Okay. So if you see what is happening, you have a sample. If you see this pen, you have, suppose this is a sample. So you have this sample, then this is under load, right? So it is going to bend. So I have now bended the pen, right? Now the bottom part is in tension and the top part here in compression. Okay, so bottom part is in tension and top part is in compression. Now we are also rotating it. Okay, you have a motor, so your sample is going to be rotated like this. Okay, but remember your sample is continuously under tension. So the as soon as the top part comes to the bottom part, right, that particular point is now under tension. So each point is going to be under tension, compression, and that too in on positive sigma as well as negative sigma. Okay, and that is what I have shown here in this particular image on the left side. If you see, the top part is always in compression and bottom part is always in tension, and since you are rotating, each point on the sample is continuously going through plus and negative stresses. Okay, and that is how we get R equal to -1, and this is called reversed bending fatigue test or RR Moore type fatigue test. Okay, so remember this is only for R equal to -1. Now what happens when you want to have different R values, right? This is a special case where the stresses are same, both maximum and the minimum, but on the negative side. So you can use what we have used for say tensile testing machine, but now we will use hydraulic system because you have to give some frequency to perform fatigue testing, right? So instead of having 4-point bend test in RR mode type specimen, now we will have a specimen like this, like we used to do in tensile testing and then do fatigue. Okay, so you can have tensile, you can have tensile compression also, isn't it? And this is the equipment we have in the lab here at IIT Kanpur, where you can do fatigue testing. This is a hydraulic system. Okay, so your sample is going to be now in the vertical condition. Say something like this. And then you have can drip here and drip here and then do fatigue testing. Okay, so R can vary here depending upon whatever the requirement is. Remember again, R is equal to -1 for RR mode type specimen, but in this case, R can vary. Okay, now let's talk about Ascent curve, where S is your stress, N is your number of cycles. Okay. So here what we are doing, we are plotting stress, which is S, with number of cycles, and typically in log scale. The number of cycle is in log scale. Okay. Now here S can be sigma A, sigma max, or sigma mean. But typically we use either sigma max or sigma A when we plot it. Okay. And what we get here from this diagram is fatigue limit or say endurance limit. Okay. Or the second one is fatigue strength. I'm going to explain this too. Okay. So basically what you are doing, suppose you are performing a test where N is here on the x-axis and then S, and let's say this is sigma amplitude, okay, on the y-axis. Okay. And this, as usual, I have told this will be in most of the cases log scale. Now, if you start with the very high stress or high sigma amplitude, right, or say sigma max, right? It is going to require some number of cycles, right, for material to fail. So let's see that it failed here. Okay, and it took a number of cycle which is say N1 corresponding to S1. Okay. Similarly, we can decrease the stress, and then obviously if we decrease the stress, the number of cycles to fail is going to be higher, right? So N2, and then you have S2. Similarly, you can get lots of data points. Okay. So what you are doing, you are performing a test with different stresses, right? Or stress amplitude, or say S max is given, right? So whenever the material fail at that particular stress amplitude, you note down the number of cycles to failure, and then you plot it. And whatever curve you get is actually Ascent curve. Okay. So remember, here in Ascent curve, we are not talking about initiation and propagation. We are talking about number of cycles to failure. So this N is number of cycles to failure. Okay. So if I assume that, Ni was my number of cycle for initiation, and Nf is the extra number of cycles for failure, the total number of cycle for failure will include Ni plus Nf, right? Okay. So remember again, the ascent curve doesn't talk about the initiation and propagation. It includes both initiation as well as propagation. So what we get finally is the number of cycle to failure. So you take a sample, you do fatigue testing at certain amount of stress, you note down how much cycle it has taken to fail, and then you plot, stress versus number of cycle to failure, you get ascent curve. So basically there are two types of ascent curves you are going to see, and many books will talk about that. So the first one is where after certain amount of stress, your curve becomes almost flat. So now let me write down is an F, where F denotes failure. So number of cycle to failure. Okay. So this is curve 1. Another one is it continuously goes down as you decrease the stress. So it doesn't become plateau. Something like this. Okay. So this is say curve 2. This particular curve, the curve 1, right? We get typically for BCC steels and titanium alloys. And curve 2 is for FCC metals and alloys. For example, aluminum alloys, magnesium alloys. Okay. So if you see curve 1, after a value of stress, right? Say this value, right? Below this value, the material is going to sustain the number of cycle. It is not going to fail, right? That is what this particular plot says, that if you are, say in this particular NF value, it is going to fail, right? But, or if say this particular stress, say I would say S1. Okay. So if you are at S1, it is going to fail. If you are at SE, it is going to fail. But if you are below SE, it is going to not fail. That is what this particular curve suggests. I'll come back to this particular point, not fail, again in a bit. Okay. Now this particular value SE is called endurance limit or fatigue limit. Okay. So if I write down the definition of endurance limit and fatigue limit, is the stress value below which the material can sustain infinite number of cycles. Okay. So this stress value is called endurance limit. That is what this curve predicts or this curve shows, right? That if you are say in this particular region, S2 is not going to fail, right? Infinite number of cycles. I'll come back to again this particular curve. Now let's come to curve 2 where the stress is continuously going down. Okay. Now there is no concept of endurance limit here because at each stress you are going to have number of cycle to failure, right? So if we are at this particular point, you are going to fail, your material is going to fail. If you are again say S2, your material is again going to fail at certain number of cycles, right? So we define a term called fatigue strength for these kind of materials. Fatigue strength. Okay. And this is the strength or stress corresponding to 10 to the power 7 cycles. Okay. In some books, you will see 10 to the power 8 cycles, but here we will just stick to 10 to the power 7 cycles. Okay. So let's say here. So if I have 10 to the power 7 cycles here, right? So whatever the stress value is, we call this stress value as fatigue strength. Okay, this particular value here. Okay, so you have two types of curves. One will give you the endurance limit, especially BCC steels and titanium alloys, and another one where your curve is continuously going down. We talk about fatigue strength and not the endurance limit or fatigue limit. Okay, and the fatigue strength corresponds to 10 to the power 7 cycle. Okay. Now, if you go through papers, they talk about why do you get this difference in these two curves, right? So many people have thought about that, these BCC steels and titanium alloys, they have interstitial atoms. Like titanium alloys have oxygen and BCC steels, obviously, they have carbon and nitrogen atoms. And because of the strain aging phenomena, you are going to obtain a curve which is type 1 in BCC steels and titanium alloys. So if you are at higher stress value, you have sufficient stress to overcome the pinning effect of these interstitial atoms. But if you are at lower regime, you are not having sufficient stress to accumulate the cyclic or fatigue damage, right? So that you can overcome the effect of these solute atoms. And that is what many people have thought about. But recently, last decade, people have also talked about very high frequency fatigue testing, where the frequency typically, when we do in the lab, the frequency is 20 hertz, 40 hertz. But now you have equipments where you can go to ultra high frequency also, right? So you can do tests at very, very high frequency, and that means limited amount of time. In very short time also you can do tests. And there are papers which actually talk about that in fact there is no fatigue limit for these kind of materials. The only reason why we are getting the plateau curve is because you're not giving sufficient amount of time or sufficient number of cycles for fatigue damage to accumulate before you stop the test, right? So because of the advent of all this very high frequency fatigue testing machine, people have shown that in steels also you are going to get a curve which is going down, but you need to have very, very high number of cycles, which we typically avoid, if you are going to do in 20 years or 40 years, in conventional machines. So I will show you those two papers. Okay, so if you see, you have the first one is beyond SCF, right? Beyond high cycle fatigue. Is there a fatigue limit? So this is by Berger, and I have given the link. So those who are interested, they can go through this link. And the same authors, these three authors, they have again published a paper in 2011 in International Journal of Fatigue. The title is Very High Cycle Fatigue. Is there a fatigue limit? Right? So they have shown that if you give sufficient number of cycles, sufficient number of time, you are actually going to get a decreasing curve, which we typically do not observe when we conventionally use, low frequency fatigue testing like 20 hertz, 40 hertz, etc. in the lab. Okay. So that is what I wanted to discuss about two types of curves. Okay. Now let's talk a bit more about Ascent curves. If you again plot it quickly, right? So you are going to get, say, some curve like this, right? So typically, if my number of cycle is low, at which it can fail, so we call it low cycle fatigue. Okay, and typically it is 10 to power 3 to 10 to power 4 cycles. Okay, and above that we will call it as high cycle fatigue. Okay, so when we talk about low cycle fatigue, you are in higher stress regime, right? And typically we say that if we are in low cycle fatigue, you are typically above the yield point, right? And the plastic strain, right? And when we are at high cycle fatigue, the number of cycles to fail is high. You are in the low stress regime. So you might be in elastic regime also, right? You are actually in elastic regime when we talk about high cycle fatigue. And we will eventually discuss why in elastic regime also you are going to get fatigue failure, right? Typically, we don't observe that in uniaxial tension. Okay, so this is how you differentiate between low cycle fatigue and high cycle fatigue. Now, one important aspect is, the statistical nature of the fatigue test. Typically, you need to perform a very large number of samples for to get Ascent curve, the accurate Ascent curve. Okay, because fatigue can start from the surface, as I have already mentioned. So when you have the samples, you have lots of variability in terms of the surface characteristics. Okay, so the number of cycle to failure varies between sample to samples, even if the stress is same. So you need to perform lots of fatigue testing on the same alloy I'm talking about, right, to get Ascent curve. And the variability, it actually is higher at lower stress regime as compared to the higher stress regime. And the reason is when you are at lower stress regime, the initiation becomes very important. Okay, and when you are at higher stress regime, initiation is much faster compared to when you are at lower stress regime. Okay, so when the initiation becomes very important, and initiation is most probably is occurring at the surfaces, right? That means you are going to have lots of variability when you are at lower stress regime. Okay, so that is one important aspect of fatigue testing, that if you want to do Ascent curve, if you want to get Ascent curve, you have to do lots of samples, Okay, now let's talk about how do you represent Ascent curves. So representation of fatigue data. Okay, so you have NF on the x-axis, and let's see, we are plotting sigma max, and you have done experiments at different R ratio. Okay, so let's say you have done at R equal to plus 0.3, R equal to 0, R equal to minus 0.3, and R equal to 1.0. Okay. So if I do the experiment at different R ratios, you are going to get different plots, right? Because the stress range, etc., sigma max is also going to be different. Okay, so the stress parameters are different. So obviously your Ascent curve is different. So now let me plot. Roughly, it is going to be say something like this. So rough, huh? So this will be for R equal to 0.3, R equal to 0, R equal to minus 0.3, and then say R equal to minus 1. This is minus 1. Okay, so now how do we understand this? What is happening here? So what we see here, that the number of cycles to failure is going to decrease, right? If you decrease the R ratio, right? So now let's understand this. So let's say sigma max is equal to constant. So let's say this particular value. So sigma max is equal to constant here. Okay. And I'm going to extend this curve for better understandings. Okay. Right. So what you observe here is that at R equal to 0.3, your sigma max is constant. So at R equal to 0.3, NF is higher, right? The highest, and R equal to minus 1, NF is the lowest value. Okay, and sigma max is constant. So let's make two plots. Okay, so let's compare with R 0.3 and 0. It's easier, right? So you have a fatigue cycle. So I'm making sigma max constant, and one is R equal to 0.3. So let's say this is R equal to 0.3. Another one is R equal to 0. So if sigma is equal to 0, and this is your sigma max. So sigma max is constant. So for R equal to 0, your curve is going to look something like this. Right? So if you remember, when we discussed about the factors affecting the fatigue behavior, the first point was the process parameters, where in that the first point was sigma max. Right? Now sigma max is constant. Second point, if you remember, was the variability in the maximum stress and the minimum stress, the difference, right? So if you see, when R is equal to 0.3, the sigma R is this. And when R equal to 0, your sigma R is large, right? Okay. So your sigma R is greater for R is equal to 0 as compared to R equal to 0.3, right? What does it mean? It means that the number of cycles to fail is going to be less R equal to 0. And that is what you observe here. See on the left diagram. Right? So using the schematic, you can actually understand what is going to happen when you change the R ratio. Right? So that is how we represent the fatigue data when R is varying. Okay? Now let's see another representation where we are plotting sigma A, which is alternating stress. And then NF on the x-axis. Right? So now we have 4 curves. It's something like this. And we are varying mean stresses. So sigma 1, sigma M2, sigma M3 and sigma M4. So we are varying mean stresses. Okay. And in this case, sigma M1 is the lowest and sigma M4 is the highest. Now let's understand using again the schematic why it is happening. Okay. So now let's take the same value of alternating stress. So I'm taking say this particular line. Okay. The same value of alternating stress and we are varying now the mean stress. So now let's talk about sigma M1 and sigma M2. So sigma M1 is less than sigma M2. Okay. So say we have this particular fatigue cycle where alternating stress is sigma A, let's say 5, so that we don't get confused. Okay, so sigma A 5 is your alternating stress, and for this we have for sigma M1, this is the particular situation you have, right? So this is your sigma M1. Okay, now let's see what happens when you increase the mean stress, which is sigma M2. But remember, you are keeping the alternating stress to be same. So this we cannot change. Sigma A5, right? That means sigma R is also not going to change. Okay? So if you want to increase the mean stress, the only way it can be done is that we move the curve upward, right? So suppose y-axis here is your stress value, sigma or S, right? So the only way it can be done is that we move it upward, but keep the alternating stress same. So this remains as sigma A5, but now mean stress has changed to sigma M2. So this particular value is sigma M2. And if you see the feeder, you know it sigma M2 is greater than sigma M1. Okay. Now what is changing here? Alternative stress is same, but if you see sigma max is higher where? So for sigma M1 case, your sigma max is this. So let me write down sigma max 1. And for sigma M2, this is your sigma max. So sigma max 2. So sigma max 2 is greater than sigma max 1. Now again, go back to the factors affecting the fatigue behavior. What was the first point? If you increase the maximum stress, you're going to see earlier failure, right? And that is what you see here on the left side. If you see sigma M1, the number of cycle to failure is say NF1. Sigma M2, the number of cycle to failure is say NF2. So NF1 is greater than NF2, right? Or opposite side, if you increase the mean stress, the number of cycles to failure is going to decrease, right? And this is happening because we are increasing the maximum stress. Remember, we are keeping alternating stress same here, the concept what I just discussed. Okay, so if you know the concepts of R ratio and alternative stress, all these stress parameters, we can draw the schematic and then try to understand why the number of cycle to failure is either going to increase or decrease, okay, depending upon the maximum stress value and the alternative stress. Okay, so we'll stop now and we'll meet next time. Thank you.